Hi, Chem. It's about that time of the unit again, eh? Review video. You can tell y'all are stressing. So as you can see, I have a central reaction already set up, which is the decomposition of ozone. Uh, right now, as I'm recording this, it is 11:42 p.m. I would like to go to sleep soon. So, if this video is a little bit short, that's why. Uh, I probably will keep the video the standard length, mainly because, well, so much stuff in Unit 5, and so, you know, that, yeah. Anyway, let's get started, shall we? So, first up, reaction rate. So, this is the unit about kinetics. Now, if any of you have taken Physics 1 or know LG in general, you would know what I'm about to say. But if anyone hasn't taken Physics 1 or doesn't know LG, this kene, comes from the Greek, or comes from kinesis, which is motion. Kinesis. Uh, which means kinetics is motion, or in the chemical sense, rate. And this rate, uh, if you think about anything having a rate, really, it means that it is what you're measuring, MEA, well, we'll say, divided by some time t. Right? And this is sort of what kinetics is all about. Kinetics really measures a rate of reactions, which are, and so for our decomposition reaction here, the rate would be measured as uh, a derivative, quite literally, actually. If we draw a concentration CVT versus time graph, uh, well, let's say C oxygen, right? And I'm gonna use the little brackets here. We'll see something like this. Now, the average rate, I'm assuming most of you, or if not all of you, have taken some sort of calculus. However, for those of you that haven't, the average rate is literally just what's the slope of the line that it takes to get from point A to point B, right? And now I am going to crush some of your hearts right now because of this. Now, those of you that have taken calculus have already started to groan because this is what is known as a derivative. This is also known as the instantaneous rate. There is a lot. AP doesn't expect you to know the calculus behind it. Just know that there is calculus behind it. Uh, then that is the instantaneous rate. Now, rate is always measured in molar per second, or molar per unit time, really. It doesn't have to be second. It could be second, minute, time, year, decade, century, millennia. Uh, Usually, we limit ourselves to seconds, minutes, hours, and years because that's what's on the human time scale. Uh, excuse me. I'm coughing a lot. It's late, so anyway. So we can measure our rates per se. Uh, so say we have the rate of disappearance appearance of ozone O3. Um, for this example, we'll just say that it is 10 molar per second. It seems like a lot. It's not really. Remember that these are both gas phase molecules at room temperature. They are whizzing around very fast and they have a very high concentration. Uh, so that would mean that this would have an appropriate rate of appearance of O2 as 15 molar per second. And it can actually go both ways. Now the reason why I say that this is 15 and not something else like 11 or 20 is because of the stoichiometric ratio. If we write our reaction out here, you can see that our stoichiometric ratio is 2 to 3. Now, if that means for every two ozone molecules that disappear, 3 oxygen molecules appear, which means that the rate is always going to be in a ratio of 2 to 3. Now, on to our next topic, which is the rate law. The rate law basically tells you the rate for a certain reaction, sort of. Given concentration and stuff, right? So let's go ahead and set up a hypothetical reaction here. AA plus BB turns into CC plus DD. Now, the rate is equal to the rate constant, and here's the really important thing. The rate law is always determined by experimentation. From the balanced reaction, you can never tell from the balanced reaction to the rate law. Now, sometimes you might get lucky, and the balanced reaction just so happens to have the coefficients for it, but in general, it doesn't. So, we'll say that the powers are n and m. Right? So this would be our rate law. Now, this is the rate constant K. It is multiplied by both the concentrations to ensure that the rate matches experiment, and its units depend on the order of the reaction. This order of the reaction that I'm talking about is basically like if you double a reactant, by how much will the rate of the rate of reaction increase, right? Usually, and this actually directly corresponds with these numbers up here, right? So N and M, these are orders of reaction. The most common way to find them is by doubling one and leaving the other constant, which is why on the AP test you'll often see tables that will look like sort of like big rectangles. All right, and then I'm gonna make up some data so that I can give you a good example. So let's make this our A and B. All right. So concentration A and B. All right. Well, yeah, concentration, and then these columns will be the rate. So if let me just this is the rate, and this will be A, and this will be of B. So let's go ahead and do a couple trials here. So let's say that our hypothetical scientist goes and does, how many trials can I fit in here? 5 trials. Let's say he does 5 trials. Shut up, computer. If he does 5 trials of 0.01 molar, 0.02 molar. Actually, this is a very bad table to do this with. I just realized. Again, I'm tired. So what you'll actually most likely get is something like in a concentration rate. So B, right? So let's say that A has a concentration of 0.15 and B has a concentration of 0.1. That would have a rate of, say, 1.7 times 10 to the negative fourth molar per second. Now, if you double A, 0.3, and keep B constant, this would be testing the reaction order. In this case, let's say that doubling A gives us a double in reaction rate. This would be 3.4 times 10 to the negative fourth molar per second. Now, this would be a first order reaction in A, because when we doubled it, we got a double in reaction rate. Now let's go back and down to A being 0.15 molar, and let's double B, 0.2. We shall say that B will have that doubling B will have an effect of 6.8 times 10 to the negative fourth molar per second. Now, this is a quadruple of this rate, which would mean that the reaction is second order in B, because we squared because it is by what our factor is squared. So if we doubled B, we would get 4 times the rate. If we triple B, we would get 9 times the rate. Alright, so the K now depends on the total order of the reaction, which you get by just adding by adding N and M up. Total order, you can think of, is equal to N plus M. And now this K is dependent on this total. So if the total order, and then I'll just put units here. If the total order is 0, then the units are just going to be molar per second, because rate is equal to K. If the total is 1, then the units are going to be 1 over second, since 1 molar component is going to be multiplied by K, giving us a rate. If the total is 2, then the reaction rate would be 1 over molar second, since you have a molar squared. 3, 1 over molar square second, and so on and so forth. You get the idea. And we can actually make something else called an integrated rate law, which the derivation is actually quite confusing and requires differential and integral calculus. I won't do those tonight. If you would like me to do them, I can upload a video of just me doing the derivation. However, I will not include the derivation in this video. Bottom line is, for our zero order reaction, the integrated rate law would be A at time t is equal to negative kt plus A at time 0. For the first order reaction, we have the natural log of A at time t is equal to negative kt plus the natural log of A at time 0, sorry. And our second order reaction is 1 over A at time 0 is equal to kt plus 1 over A at time, there should be t, A at time 0. And these are all the integrated rate laws that you need to know for the AP exam. There is probably one for third order. I don't know it. It's also probably really hard to derive as with the other two. Therefore, I'm not going to show it. So that was rates laws. And actually, I forgot to mention something. We can actually use these to determine half-lives. Now, really, what we're only going to do is first order, in which the time for the half-life is 1 natural log of 2 over k. Now, what you can do, the types of questions, right, would be given half-life, and initial concentration, find the time to some final concentration, right? Now, what you'll normally do is you'll find K. So what you'll do is you'll take your T half, and then put that under ln2. That gives us K. And then from that, we can determine time to get a T by taking e to both sides and yada yada yada. You get it. So this is how we can use rate laws in the College Board questions. Unsurprisingly, College Board will make this as quite simple. However, with the rate laws, the questions actually can become quite simple. So now let's move on to elementary reactions. So elementary reactions are in fact what the reaction rate is based off of. However, you have to get the reaction rate law first in order to get the elementary reactions. So let's say, for our ozone example, we'll say that O3 plus NO turns into NO2 plus O2. And you might be shouting at your screen, but Larry, I don't see an NO or NO2 anywhere in the reaction. I know. That's because this is an elementary reaction. It is a reaction that has to take place at a time. You can't break this up into multiple different reactions. Now, we can write another elementary reaction for this. NO2 plus O3 turns into NO plus 2O2. This is another elementary reaction. And in fact, these are both related. So for mechanisms, so let's say that this is a fast so if we call this the slow step, and if we call this the fast step, then we can actually find out the rate law. However, if we change that to an equilibrium and switch these around, we all of a sudden have to do some more math. So let's go ahead and switch this around so that it matches real world. This is fast and this is slow. So, let's first start by setting some ground rules. Rule number 1: no intermediates. If you have an intermediate in your rate law, College Board will count it as wrong. Okay? Rule number 2: the slow step determines your rate law. Alright, so let's go ahead and follow our rules here. So first step, slow step determines rate. So the overall rate of this reaction is equal to K times NO2 times ozone. Now let's check. Do we have the slow step determining the rate? Yes. Do we have any intermediates in our rate? Yes. Now, intermediates are very bad to have in a rate law. They are intermediates will mess you up, and you will lose points. So to counteract this, let's go ahead and look at our first reaction. We're going to use a method called pre-equilibrium approximation. Basically, this says that the rate forwards is equal to the rate backwards. Or rather, or in other words, this top reaction reaches equilibrium before the bottom reaction can finish. So, we can say, essentially we can say that O K, we'll say 103 times NO is equal to K2 NO2 times O2. Now you'll notice, actually let's form this into K minus 1. Now you'll notice that K minus 1 has that NO2 that we're looking for. Hooray! So let's go ahead and substitute that one. And let's go ahead and solve for NO2 here. So we then have K1O3 times NO over K negative 1 times O2. Now this is equal to the concentration of NO2. So now we can plug this back into our rate, making this the rate of our reaction. K times O3 times NO times O3 all over O2. We combine like terms and we get rate equals K times O3 squared times nitric oxide, or NO, all over O2. And now this would be our rate law for our reaction. And this would be our reaction mechanism for our rate law. Keep in mind that the rate law has to be determined experimentally, or rather the order has to be determined experimentally. The mechanism is what happens after. So let's go ahead and start on the next big tenet of this unit, the collision model, or collision theory. Let's say we have an O3 molecule, right? Ozone. And I'm using the space-filling model for a reason you'll see very quickly. So our space-filling model allows me to have N here and O here. Now, collision theory states that a molecule must have sufficient energy and sufficient orientation in order to react. So this basically means that not all collisions between molecules will have a reaction, only some will. Now in this case, we'll say that this is going to be the result of the collision. And in fact, we can actually draw a little something known as an energy diagram. And I'll just say ET for now. Now let's say that this is the original energy of the reactants, and this spikes the energy. This is known as the activated complex. Now, if you have sufficient energy, you can form the new compounds of oxygen gas and nitrogen dioxide. Alright? And this releases tension. I've just made a very bold claim here that the reaction is exothermic. You can see that I am releasing energy here. Okay? Keep in mind that the y-axis is energy, and so this is what we call the activation energy, or EA. This is going to come up in Unit 6, and it's called delta H. All right, you got that? Good. So, uh, now let's go ahead and do the whole reaction. All right. So let's go ahead and clear the screen. So now we've just looked at an energy diagram. So if we go ahead and do the whole reaction on an energy diagram, right? Gonna make it super long. Time and energy. So let's say that this is the original energy of our reactants O3 and NO. This will be the energy of our intermediate. If you remember, that was NO2. And then we mix it with more ozone that has a huge spike, and then it tapers off. This is known as a multi-step reaction energy diagram. So what this is signifying is that we can actually sort of think of it like a ball. If you have a ball here, it takes some energy. We'll call that the activation energy. EA. It takes some activation energy in order to get the ball here. And it takes yet more activation energy to get the ball down. We'll say that this is EA2. However, you'll notice that this one was our slow step. And this also has a higher energy peak. So the slow step will always have the highest peak. Well, the slowest step will always have the highest peak. Anyway, now let's go on to some more energy diagrams for some more chemical applications. So we shall say that since our NO was used and then regenerated, right, and it appears nowhere in our equation, we call this a catalyst, something that is used and then regenerated. So what a catalyst really does, if we draw an ET diagram, if we mark the uncatalyzed reaction, you'll see that it has this huge spike, right? Very big spike, almost impossible to get enough energy to clear that. However, with a catalyst, as I'm going to mark with the dashed line, this spike is more of a hill now, and it takes less energy in order to get there, which means that our things have to line up at the same point, and also that we also have the same reactants and products. We just take a different pathway, which is basically what a catalyst does. It opens up a new pathway that takes up less energy. Thank you for watching. It's 12:11 right now, and I hope that you ace your exam. Goodbye.